Avoiding a train wreck. We've been looking at decision trees, but decision trees have many shortcomings. We also have another classifier, if you remember, and that's the k nearest neighbors. But in both of these, we have to worry about overfitting. And so to deal with overfitting and the problem of false positives and false negatives, we need to use what are called validation and testing to avoid a training wreck, if you want to think of it that way. So remember from last lecture, we looked at these two examples. Who's getting dessert? Should I buy this car? We had true positive rate, false positive rate, as you see down there. But this was only for the training set. So let's suppose we include validation and testing. So what do we mean by that? Well, let's just recall, we've already talked about this a little bit, but remember, we can take a set of data and we can break it into three parts. And a lot of times we take, for the actual design of a classifier, an entire training set itself, and we might break it into three parts. The training set to build the classifier, the validation set that's used to tune or test the classifier as it's being constructed, and finally the test set, which is used to actually determine how well a classifier performs. So we design based on the training set, tune based on the validation set, but we accept or reject whether or not we should use such a classifier based on the test set. Now, for example, let's suppose we chose 20% as a test set. So 80% of the data is going to be used for training and 20% for testing. So here we have our confusion matrix for the car and for the dessert. And notice that for the should I buy this car, it looks pretty good. For who's getting dessert, well, not so great, but you know, let's see what we get. So for who's getting dessert, we have a true positive rate of 0.111 and a false positive rate of 0.133, and the first should be close to 1 and it's not. The second should be close to 0 and it's really not. In contrast, let's look at should I buy this car. The true positive rate is 0.857. It's not terrible. And the false positive rate is 0 here. Well, that's because you can get. Now let's notice something else. The dessert data, when we partition it into 80% training and 20% testing, we actually wind up with a different tree classifier. So here's the same data set with 100% of the data compared to the decision tree we get with 80% of the data. And notice I'm using the new rattled way of drawing decision trees to better illustrate what's going on here. Let's suppose we randomly selected another 80% from the training set. Then with 100% of the data, we have that. And now we have, with a different random selection of 80% to be the training set, we get an entirely different decision tree. And we do it again, yet another kind of decision tree. However, if we look at the car evaluation data, when we partition it into 80% training and 20% testing, the classifier that we get from the training data is about the same as we got when we used the entire set of data. So here's with 100% of the training set as compared to with 80% of the training set. So pretty close. Measuring on test sets in particular allows us to reject poorly performing classifiers. Remember that big data is cursed, and part of this curse is that classifiers will always produce results. So we'll always, given an unlabeled observation, get a prediction of it's in one class or the other. So that means we've got to have ways to measure whether or not the classifier is making good classifications. In particular, that means we've got to differentiate between making an algorithm work, which has been our emphasis to this point, and measuring an algorithm's performance, which is new in this lecture. For example, in the last lecture we concentrated on making algorithms work, And probably none of us realized that the car data classifier was much better performer than the dessert data classifier. But now we know. Measures on test sets also allow us to assess the data itself. Remember the curse. High volume, high variety, high velocity. These hide the nature of the data from us. So if we get poor results, it may be because of the data, not because of the method we applied to it. Another way to think about that is there really are no bad classifiers, but we could choose the wrong classifier for a particular problem, and it could be that the data is such that no matter what classifier we predict, it'll be a poor performer. So we work with extremely large data sets, but believe it or not, the biggest problem we have is that data sets really aren't large enough. So for example, in the getting dessert data, we really don't have enough variables to answer the question to accurately predict who's getting dessert. There are many issues that we would like to have measurements for that we suspect would probably have something to do with the decision. Are they dieting? Are they eating late? Is it the weekend? Is it cold and rainy? Are they overweight? So all of these influence the performance of the who's getting dessert data, but are not reflected in the data set. Now that leads to an issue of stability, or particularly instability. So if we have small variations in the training set, then we could get large variations in the classifier or in the classifier performance. And that's an issue of stability, and we've already seen it with the dessert data. Another issue we often address with testing is overfitting. So a classifier could be so entrained to a particular training set it fails to predict non-training set observations, in particular those in the test set. So to begin with, let's suppose we just had a data set. So we're not talking here about big data or classifiers, just in general a data set. We could pull some points out for a test set from the original data set. And then it's easy to see that if we take out the test set and we use a method, for instance some kind of a high degree polynomial fit, we could actually get something that fits through every single point. Now you might say, well gosh, that's about as good a fit as you can get, isn't it? And actually no, it's terrible. Notice the predictions for these test set points are on this blue curve, and the blue curve is so entrained to the data that it's a poor predictor of the test set. On the other hand, these very poor predictions could be much improved if we simply used, in this case, a regression line. And now you can see we get better predictions of the test data. In this example, linear is better. Let's look at the analogous idea for a classifier. So we've got two classes, ones and zeros, and we've got some test data. Overfitting might mean that we're so fit to the quote boundary of the class 1 data that when we then look at our performance on the test set, in this case we only have 50% accuracy. Here's another example where we've overfit to the 0 class, and once again we have only 50% accuracy. So both of these are examples of overfitting, and it's revealed by the classifier and testing of the classifier. And just parenthetically, this is a separable problem, but we would have to embed this in a higher dimensional space to actually solve this problem, because it's not linearly separable. Another issue we can address with testing is bias. You can find about any pattern you want in a big data set, and therefore there's a tendency to bias the results. So for example, in the dessert data, we could easily justify almost any a priori belief we have. We could go in and say, well, vegetarians never get dessert. We could pick out patterns that supported that. Those who order red meat and drink soda will get dessert, and so on and so forth. But the key is the metrics have already shown that we really need to reject the classifier for who's getting dessert. We shouldn't use it to say anything. based on our metrics. There's a lot of others, many of which are related to information and entropy, and we'll look at some of these later on.